Hello, welcome back. In our previous videos, we've been exploring collections of discrete objects, and now we're going to develop techniques to count them. The study of counting techniques is called combinatorics. As you'll see, it requires a different kind of thinking. The key to counting well is to understand the structure of what you're counting. Now, there's a distinction between the concept of counting and enumerating. When we talk about counting objects, the answer that you'll get is a number. On the other hand, if you're enumerating objects, the answer will be the list of objects that you're counting. And in fact, sometimes the best way to count things is actually just to list out all of the objects. For example, let's say we were trying to count how many months have 31 days. A strategy to approach that question would be list out all the months and determine which ones satisfy the criterion that they have 31 days. Here we've enumerated all the months, and the ones with 31 days are January, March, May, July, August, October, and December. And so if we count the check marks, the answer is that there are 7 months with 31 days. We'll get to some counting word problems in a minute, but first let's answer a simpler question. How many elements does the set 1, 2, 3 up to n have? Well, hopefully we all know the answer to that. If we start counting 1, 2, 3 and we go up to n, we've counted n different numbers. What happens if we start from 0 though? We know there are 10 numbers between 1 and 10, and so if we have a 0 in there, there's going to be 11 elements. Now what about the set a plus 1, a plus 2, all the way up to b? That includes any set of consecutive integers, not just ones that start with 0 or 1. One way we could count that is to rewrite this set as a plus 1, a plus 2, all the way up to a plus b minus a. If we subtract a from each of these elements, we get a minus a is 0, a plus 1 minus a is 1, all the way up to a plus b minus a is b minus a. And we learned above that the number of elements in this set is b minus a plus 1. So for any set of consecutive integers that starts off at a and goes up to b, the number of elements is b minus a plus 1. So you want to be careful about this, because a natural expectation is that the answer would be b minus a, but there's always this plus 1 hanging around. So if we look at this set, we take 42 minus 23 plus 1, which is equal to 20 elements. When you're comfortable with this rule, that allows you to count sets of objects that can be indexed. Sometimes there's some logical number associated to every object that you're trying to count. That's called an index. When the indices correspond to a set of consecutive numbers, this can help you count the set. Consider this set, 13, 15, 17, up to 99. We see a pattern in this. We see that all these numbers are odd numbers, which means they're of the form 2k plus 1 for some integer k. 13 is equal to 2 times 6 plus 1. 15 is equal to 2 times 7 plus 1. 17 is equal to 2 times 8 plus 1. And if we continue, 99 is equal to 2 times 49 plus 1. These numbers, 6, 7, 8, up to 49, can be thought of as the indices of each of these numbers. And that means we can count them. There are 49 minus 6 plus 1 elements in this set, which is 44. Now look at this example. We want the numbers 26, 37, 50, 65, going up to capital N squared plus 1. Now that capital N squared plus 1 is a good hint. I look at 26, and that is 25 plus 1. And 37, that's 36 plus 1. And 50, that's 49 plus 1. And 65, that's 64 plus 1. Each of these numbers is of the form k squared plus 1 for some integer. The first number is 5 squared plus 1. The second number is 6 squared plus 1, all the way up to capital N squared plus 1. We see 5, 6, 7, up to capital N as the indices of this set. And so the number of elements is capital N minus 5 plus 1, which is n minus 4.